Okay, so as I'd mentioned before, we're going to be talking today about transient dynamic finite element methods. And by methods, I really mean the analysis procedures. So in some sense, I like this subject because it's a good opportunity for review. We're going to go through all the same steps that we went through before, just a lot faster because you're a little bit more familiar with them now. But we're going to go all the way back to the beginning of the class when we started talking about governing differential equations, and then we'll work our way through and propagate that into coming up with some new finite element analysis procedure that takes into account dynamic behavior. So to do that, we have to go way back to the beginning and talk about things like the balance of linear momentum, which was kind of a very simplistic topic that we'd introduced when we started trying to derive the equilibrium equations. So the balance of linear momentum is really a relatively simplistic statement of, I guess you could call it a conservation law. In a universal sense, momentum is expected to be conserved. It's one of these universal quantities like mass or energy that is conserved. And in order for it to be conserved, we have to say that if we're considering a particular system of interest, let's say this block or something that's sliding with some characteristic velocity to the right, then this block certainly will have some momentum associated with it. And we define momentum as basically just mass times velocity. It's the quantity of motion as Newton originally defined it. And momentum is really kind of like, how much inertia does this thing have? How hard is it to kind of like get going and how hard is it to stop? But on this block, not only does it have inertia, but it might also have some external forces acting on it. So for example, maybe it's sliding over some kind of frictional surface and its interaction with that surface generates some kind of sliding or resisting force. And clearly, if the block is moving and if it's sliding and there's some kind of force that's kind of resisting that motion, then there's the potential for this force to be unbalanced, right? If there's no other forces acting on this block other than the fact that it's kind of moving with some characteristic velocity, then really the only forces that we consider, the net force, in other words, acting on this block is really just this frictional sliding force. So as you might be perfectly familiar from classical physics, if we're talking about statics, the net force acting on an object that is in static equilibrium has to be equal to zero. Otherwise, that object would start moving, it would start to accelerate. Or if it was already moving at some constant velocity, then it could too also have no net force applied to it. So there's a few different conditions that we could take into account, which account for this condition of zero net force. But ultimately, the relative change in the momentum of this system can be characterized precisely through this kind of relationship that says that the change in momentum of the system really can only occur through exchanges of momentum with this block and its surroundings. And we kind of came to the conclusion that that really meant that, whatever external forces or net force is acting on this block, that force has to really be proportional to the relative rate of change of this kind of momentum of the block. So force, interestingly, had the interpretation as being not just kind of like this thing that you can go into a laboratory and measure by kind of like hanging weights off of different measurement devices. Force is really a measure of the rate of change of momentum. It's another way to think of it is a momentum flux. It's kind of like, the rate of momentum transfer that might occur between two objects that are in contact. And the requirement of Newton's third law that forces be equal and opposite in some kind of, reaction force situation is another statement that, if this block is interacting with this surface and it's losing momentum, that momentum doesn't go into nowhere. It actually goes into, the ground that it's interacting with. So momentum conserved in this universal sense. And we could pose that statement as basically, this expression, dp dt equals the sum of forces acting on this block. And if we make a further assumption that this block is a solid object that consists of some finite amount of mass, and if we assume that the block isn't losing mass It's kind of staying the same. It's not being created or destroyed. It's also a conserved quantity. Then we can rationalize that the rate of change of the mass of this block is also going to be 0. So we can kind of say, okay, well, get rid of that term. So if I'm talking about the rate of change of momentum of this block, really what I'm talking about is the mass of this block times the time rate of change of the velocity, or in other words, the acceleration. So all of this is probably well familiar to you, not to kind of beat you over the head with things you probably already know. That ultimately, if we make this assertion, we can come to the conclusion that for a block that doesn't lose mass or gain mass, we can say that the net force acting on this block is proportional to the mass of the block times the acceleration of the block, or the rate of change of the velocity of the block. Okay, so that's Newton's second law. I'll review, and we can define all these quantities. I'll kind of reserve symbols that involve like a superposed dot to mean a time derivative. And this isn't where we ended it when we were originally talking about this subject of deriving equilibrium equations and things like that and conservation laws. This was a statement of equilibrium that really is descriptive of the block as a whole. It's kind of appropriate if all we really cared about was the rigid motion of this block without considering things like, well, are there maybe minute vibrations happening interior to the block? And do we really need to look at those details? So if you only cared about rigid dynamics of the system, then this equation would be perfectly suitable. But of course, we're talking about continuum mechanics. So we don't just want some statement of momentum conservation that applies to the block as a whole only. Really, we want a statement of momentum conservation that applies at each individual point interior to this block. So it's kind of like we need to come up with some governing differential equation that is sort of equivalent to this same statement, but which holds for any infinitesimally small subset of this block. And in fact, it must hold for any infinitesimal kind of small subset within the universe at large. So in order to do that, we went through the derivation last time, so we can kind of skip over a few of the details. But the idea is we can simply pose this statement of the total momentum of the block through an integral statement. And rather than talking about the mass of the block, we can refer to the block's mass density, which I'll denote with a rho with the superscript 0. The superscript 0 is really to distinguish that this is the initial mass density of the block. And it's really only necessary to distinguish that if, let's say, the block is deforming significantly, like in the case of large deformations. Hence why I include that extra sub-0. But regardless, if the block didn't deform very much, you could just call that the density, and it's the density that you might kind of be most familiar with, taking it off of some table somewhere or wherever. In any case, we can suppose that the rate of change of the momentum of this block, expressed through this integral statement of the integral of the momentum density, its time rate taken over the full interior volume of this block, has to be equal to the net force applied to this block, which could include different contributions, including body forces, which we would have to integrate over the interior volume of the block as well as exterior tractions that might act on the boundary of the block, or exterior kind of surface forces, which, as we saw, could be related directly to the stresses that act on the surface of this block. And through the divergence theorem, we could convert these kind of surface tractions into this equivalent statement that involves the divergence of the stress tensor, right? So we kind of skipped over a few steps here, but hopefully you kind of recall some of those details. Ultimately, we came up with this expression, and through a further manipulation, saying that this kind of integral expression that on the left and right of these kind of two sides of this equal sign, we have an integration over some volume. But I haven't been specific about which volume, right? I could be talking about the block as a whole. I could be talking about a small subset of the block that could be infinitesimally small, and any particular subset of this block. So if this small subset is arbitrarily chosen, then I can rationalize that the thing inside of this integral expression, the integrand itself, has to be equal to 0 in a pointwise sense. Or in other words, more or less, the thing inside this integrand has to be equal to the thing inside of this integrand at every interior point within the block. And this is how we actually derive and came up with effectively a pointwise statement of momentum conservation or balance of linear momentum, which basically said that rather than having, as we had in the case of simple statics, we had, the body forces plus the divergence of the stress tensor had to be equal to 0 in the case of static equilibrium, right? That was our pointwise statement of equilibrium. But now we have this extra term, this term that depends on the mass density times the acceleration. And this extra inertial term is really the thing that is indicative of dynamic behavior. So if, let's say, the acceleration was relatively small, which would happen if you applied the loading to this block relatively slowly, then you could reasonably neglect this term that depends on the acceleration, and you would get back to a state of effectively quasi-static equilibrium. Now, that's a valid assumption, again, assuming that the rate of loading is relatively small, but there are certainly situations where that no longer is true, even in engineering applications of practical interest. Obviously, if you have an earthquake, shaking a structure, that is inherently dynamic behavior. And the dynamics of the response of the structure to an earthquake obviously contributes somewhat significantly to the forces that you see in the structure. Other scenarios, of course, in which you have dynamics are things like impact, where you have, very high rates of loading being applied to the structure that might kind of cause very, very sudden dynamic behavior. And another situation that I'll point to is instabilities or structures that might be initially stable up to some critical limit, like we talked about in the case of large deformations, where maybe the structure stays stable, but then at a certain point, it'll start to collapse. And if that collapse process happens relatively quickly, then effectively you would need to consider dynamic behavior to actually understand what happens to the structure as it's collapsing. If you try to run an analysis that includes some kind of collapse behavior going on, and you don't include dynamic behavior, then it'll be kind of nonsensical. It'll kind of say that collapse happens in an instant, almost instantaneously. But that's, just generally not how the world works. Once you get into those domains, you really ought to be including and considering dynamics. Okay, all that to say, now we have this more general description of conservation of linear momentum, equilibrium, if you like, but where now we don't just say that the sum of forces has to be equal to 0, it has to be equal to the rate of change of momentum, or momentum density in this case, in a pointwise sense. So given this description of, you could call this the strong form of equilibrium, if you like. This is our governing differential equation, which has to be satisfied in a pointwise sense. And the strong formulation was nice because it was, this rigorous description of equilibrium that we've derived from these very basic fundamental principles of physics. But it wasn't particularly useful if we wanted to solve finite element problems, because, it introduced a huge number of equations that we had to solve, one for every point in the structure. And, we'd have as many unknowns as we have, these equations, and it just becomes intractable. So we had to go ahead and convert this description of the strong form of, momentum conservation in this case, into an equivalent weak form statement of the same. So we could go through the manipulations, but I think it's probably worth pointing out, just kind of reviewing some of the slides that we kind of discussed in the past, to point out the principal differences that you would see. If you went back to the slides that we had before, and you kind of went through the derivation of converting the strong formulation of equilibrium, that governing differential equation, into this equivalent weak formulation statement, it would look almost identical. Everything on the right-hand side of this equal sign would remain the same. And the only difference would be, obviously, this inertial term. And if this would just be equal to 0, then we would have a balance of external forces minus internal forces, and the structure has to balance to be equal to 0 to satisfy equilibrium. But we satisfy equilibrium now in this kind of slightly different description of, not a pointwise statement of equilibrium, but rather an integral average statement of equilibrium that's weighted by this kind of funny test function, which, in the case of virtual work, you could interpret this test function to be something like a virtual displacement field. When you come to dynamics, it's a little bit different. You could interpret this quantity certainly as a virtual displacement field, but more commonly, it actually has the interpretation as being a virtual velocity field. A slight kind of variation, just tack an extra kind of time rate on that kind of quantity, but at the end of the day, it really has the same kind of meaning as being this kind of virtual field that you're kind of multiplying against each of these terms in this equation. All right, so the main difference is, and you in fact went through this procedure in one of the homeworks, if you recall. You derived this kind of weak form statement of equilibrium in the case of one-dimensional elasto-dynamics. So you would have arrived at a term that showed up in your equilibrium equations that included precisely this. So that's kind of the extra term we have to take into account that includes that inertial behavior. And if we also went one step further, if we said, not only are we considering the weak formulation of this kind of equation, but now we're also considering a Galerkin approximation to the weak formulation, i.e. A finite element discretization of this problem, in which we have some time-varying displacement field, which varies certainly as a function of position, but also now as a function of time. And that time dependence actually comes into the picture through the way that we characterize the behavior of the individual nodal displacements. So certainly we can still represent this displacement field as a linear combination of the basis functions or the finite element shape functions, these phis, that depend on spatial coordinates. And these coefficients, which previously we assumed were just kind of a bunch of constant numbers, now we presume that they can vary as a function of time. So that's kind of precisely, if we're going to talk about dynamics, we have to talk about a time history of variation in the displacements. So these displacement coefficients, the nodal displacements, are now functions of time. And if we wanted, we could also take the time derivative, or the second time derivative of the displacement field, to come up with the acceleration field. And that's precisely what shows up in this kind of left-hand side expression. If we're doing a finite element method, we have to be consistent with the way that we're actually discretizing the displacement field and this acceleration field, if it is indeed the second time derivative of the displacements. So if we do that, if we plug in these two expressions for the displacement field and this acceleration field into the weak formulation, we can make a few manipulations and come up with our finite element residual equations. And before, when we had our residual equations, it looked something like the total external forces that act on our, each node in the structure minus the total internal forces in the structure at each node had to be equal to 0. So in other words, balance of forces. Now, instead, we have something that looks like, external force at node A minus internal force at node A has to be proportional to the time rate of change of the momentum of node A. So that's kind of the crucial difference. And where this kind of time rate of change of the momentum of node A is exactly, this term that shows up on the left-hand side. So in other words, if we kind of plug in those descriptions of our finite element shape functions, we come up with this kind of weighted measure of the momentum kind of surrounding node A, if you like. So this kind of gives us a nice weighted measure of the local momentum close to node A. And if we wanted to go one step further, we could actually say that this term, this time rate of change of momentum, can actually be expressed not just in terms of this funny integral expression, but if we make a few substitutions, then we can actually transform this representation into something that looks like some matrix, which I'll call M, times the individual nodal accelerations, the U double dot sub B, if B is one of the indices of the nodes. So we have now actually an expression that says that the time rate of change of momentum is actually equal to mass times acceleration. But this mass is not necessarily just a single scalar quantity. It is itself, as I mentioned, a matrix. And same thing, these accelerations are also individually vectors. And this mass matrix actually has a funny form. In the case of finite element methods, you can kind of show that it takes on something that looks like this. It involves the integral over kind of like the whole domain, or individually over each element, which you can sum together and assemble. of the mass density times the product of the individual kind of nodal shape functions. It's a little different from the stiffness matrix. If you recall, the stiffness matrix involved derivatives of the shape functions or the gradients of the shape functions. The mass matrix, in contrast, doesn't involve gradients. It involves just the values of the shape functions themselves. So that's the critical difference. But nonetheless, the mass matrix has some analogous interpretations to the stiffness matrix in that we can kind of do similar procedures to loop over all the elements, compute individual element level mass matrices, assemble them together to kind of form this global mass matrix for the entire structure, and then kind of proceed as usual. So if we do this, if we say, here are our finite element kind of equations of the balance of linear momentum, including this extra inertial term now, we can take it one last step and suppose that we take that definition of the mass matrix that we've just introduced to replace that inertial term on the left-hand side of this expression. We can also suppose in the case of linear elastic material behavior that that internal force term is really just proportional to the stiffness matrix times the vector of all the nodal displacements. So in other words, K times U. So replace Fs internal by K times U. And if we like, rather than representing everything in terms of these indices, we can kind of transform this into a nice matrix vector format. And you'll notice that in these ensuing expressions, I have effectively these concatenated lists of the acceleration of node 1, followed by the acceleration of node 2, all of its 3 components in the x, y, and z directions, and so on and so forth, stacked into this equivalent vector, very much in like fashion to the way that we organized that vector of all the global nodal displacement degrees of freedom when we were solving simple quasi-static problems. In that case, if we had a quasi-static problem, this whole kind of matrix and vector on the left-hand side would just be equal to 0, and all we'd be left with is, Ku equals F external, right? And that's statics, basically. Now we say, let's introduce this dynamics, inertial term, and we have this now mass matrix times this vector of all of the nodal accelerations. So the only difference we introduce is that we have this new mass matrix now. We have this vector of all the nodal accelerations, and effectively we get something that looks like mass times acceleration is equal to the external forces minus internal forces, or the unbalanced forces. So before, as you might recall, this expression of external force minus internal force, we refer to that as sort of the residual forces. It's kind of whatever forces would be left over if we were to take this kind of difference. And if there was a difference, then we would kind of need to do maybe some kind of nonlinear iteration in the context of a nonlinear analysis to ensure that we drove that residual equal to 0. That was a requirement for convergence of our algorithms. Now I'm saying, well, actually, let's not just try to drive it to 0. Let's kind of say that that residual is actually proportional to the time rate of change of the momentum of this system. So that's precisely how we can kind of go about adapting a lot of the basic principles of Newtonian mechanics now into the context of finite element methods. And it requires really only including this extra term, the mass matrix times the vector of accelerations. So we've introduced this inertial term, and it's useful to actually look at this in more maybe a simple one-dimensional context before we actually think about how do we solve this system of equations that involves accelerations at all the nodes, and how do we approach that? It's much easier to say, let's just reduce this down into a simple one-dimensional problem first. So consider, in the one-dimensional case, the simplest structure you could think of. A simple spring connected to the left-hand side by a support and with some kind of finite mass m attached to the end of the spring. And to the end of the spring, we also apply some external force. For the time being, for this example, you can assume that maybe that force remains constant with respect to time. But in general, this external force could also be some general function of time. So it could be imposing some kind of time history of loading. In this case, let's just assume it's constant. But regardless, even if it were constant, assuming that the mass of this structure is non-negligible, then what we expect is, we'll get some time variation for the resulting displacement measured at the end of this spring. So U is now a function of T, the displacement at the end of the spring. And if we were to observe, well, how does the displacement of the spring change as a function of time, starting from the initial conditions that the displacement is equal to 0 at time t equals 0. And let's also suppose that, it's kind of only released at time t equals 0, which kind of implies that not only is the displacement equal to 0 at time t equals 0, the velocity of the spring is also equal to 0. So those are effectively our initial conditions, which are essential to define if you're solving any kind of dynamics problem. Not only do you need boundary conditions, now these initial conditions are additional things that you have to specify. Okay, so if we do that, we find that the behavior of the spring exhibits this sort of sinusoidal variation. A lot of this is probably review to you. But effectively, we see that this variation, this sinusoidal behavior is, oscillating about some kind of mean value that is, in fact, just directly proportional to the value we would expect to get if we were solving this problem quasi-statically. So if we assumed that, there was no dynamic behavior and we just kind of instantaneously imposed this force, we would expect the displacement to be just equal to K inverse times F external. And in fact, that's precisely what this mean value is in this kind of diagram. So we see some oscillatory behavior about this mean value that is corresponding to kind of like the quasi-static kind of behavior we would expect. But we also see this, dynamic oscillations. And the period of vibration, or basically the distance between the peaks of this, oscillatory kind of displacement function is directly proportional to what you might think of as the natural frequency of the structure. It's the frequency at which this spring would vibrate if you kind of like excited it by applying this force and then just let it vibrate without kind of introducing any additional forces after that. So the natural frequency of vibration for, at least this kind of one-dimensional harmonic oscillator is commonly denoted by basically something that involves the stiffness of this spring divided by its mass, and then take the square root. And this gives you a measure of frequency. And if you want to get, the actual period of vibration, you just take 1 divided by the frequency. But it's important to note that there's a slight distinction in the units here. Typically, when you compute natural frequency in this way by taking square root of k divided by m, the actual units you get out of this are in terms of radians per unit of time. And in order to account for this kind of potential difference in interpretation of what do I mean by frequency, do I mean radians per unit of time or do I mean cycles per unit of time? By a cycle, I mean one full kind of revolution or kind of like peak to peak distance in this sort of oscillatory diagram. So this being one cycle of revolution basically means that I have to, multiply by a factor of 2 pi. So that's precisely why I have this 2 pi factor here. But in any case, this one-dimensional equation of motion, as it's sometimes called, effectively is just exactly our finite element equations just reduced to this very simple one-dimensional example. So mass times acceleration equals external force minus internal force, where that internal force is assumed to be directly proportional to the stiffness of the spring times the displacement of the spring, both of which, the acceleration and the displacement, are assumed functions of time. So this expression is sometimes referred to as the continuous in time form of the equation of motion. It's the equation that you could theoretically solve, at least for this very simple problem, by solving this second order partial differential equation expressed with respect to time. So you can do that through very simple analytical techniques, but obviously, that really is only possible in the context of these simple one-dimensional types of problems. So how do we generalize this approach if, let's say, we're solving not just this single degree of freedom type of system? What if we have like multiple degrees of freedom in our structure, as we would have in a finite element analysis? Not only do we have a single spring that's vibrating, we have all the nodes in the structure are potentially, vibrating. So could we do the same kind of thing in solving this second order partial differential equation in that format by solving it in this continuous in time format? Well, it is possible to do that under certain special circumstances. But today, we're not really talking about that. Today, we're talking about transient dynamics. Now, if you were to solve these continuous in time equations in that format, in this particular continuous in time format, you would be doing something called a modal analysis. You'd be looking for what are kind of the natural frequencies, plural, of the structure as a whole. And there would be as many frequencies as you have degrees of freedom in the structure, as it turns out. And you could try to decompose the behavior of the structure into what's happening, not with respect to the individual nodal displacements, but in terms of its individual kind of like frequencies or modes of vibration. So you could try to decompose everything with respect to each of these modes of vibration and treat them as individually, kind of like these one-dimensional harmonic oscillator types of problems. But again, there are some limitations to doing that. It's limited to considering usually, very simple loading scenarios and linear elastic material behavior. To generalize that to, more complicated time histories of loading, and also to the case of maybe nonlinear material behavior or nonlinear geometric behavior, we have to really do something different. We have to, rather than treat this as a continuous in time equation, we actually have to discretize it in time. So instead of solving these equations in this format, we have to really pose a similar statement of conservation of linear momentum, but in sort of a discrete sense. So I'm not going to attempt to, solve this equation, at every stinking time t in some kind of analysis. Instead, I'm going to choose to enforce this condition, this equation of motion, at only a discrete number of times. It's kind of like I'm choosing a collocation method where I'm saying that I'm going to satisfy this equation at these kind of discrete values in time. And typically, this aligns well with some of the discussion that we've had previously on the subject of time discretizations. So if you're doing any kind of nonlinear analysis, it's typical to actually subdivide the incrementation of loading into multiple substeps or time steps. And in a similar fashion, now it's essential to do this in the context of a transient dynamic analysis. We have to come to this, problem and say, I'm going to actually subdivide this kind of whole time domain into a sequence of time steps, which might have finite size delta t. And I might have any number of these, but at each one of these time steps, I suppose that I'm seeking to solve this kind of equation of motion. Now, the other distinction that I want to point out is that when I do this, when I discretize this problem in time, I also have to introduce a few additional variables. It sufficed before to assume that if we're solving this continuous in time equation, then we could treat the acceleration of the structure as being just the second time derivative of this displacement field. But now in the discrete in time case, I actually have to introduce additional independent variables characterizing both the velocity and the acceleration of the structure. So I have now two new unknowns that I have to solve for at each distinct time step as well. So not only am I looking to solve for what's the displacement at each of these different distinct time steps, now I also have to solve for each of these. What's the velocity at each time step and what's the acceleration at each time step? Because they're not necessarily directly related to the derivatives, the time derivatives of these functions. If I'm discretizing things in time, it's not exactly clear what the time variation of these functions is. I haven't really specified it. I could try to use some kind of interpolation scheme like we did with finite elements, but more commonly, the traditional approach to developing these kind of time discretization procedures is to instead take a slightly different approach. So we introduce these two additional variables, and this actually introduces a complication because it means I have at each one of these different time steps an equation of motion, which is kind of the equation that I'm seeking to solve in order to try to determine what's the new displaced state of the structure at some kind of proximal time state to an existing time state that I already kind of happen to know all these variables. So the general procedure that people take in solving these problems is they suppose that you proceed in your dynamic analysis by presuming that you know the time history of loading up to some preceding time state, which I'll call T sub n. So at this preceding time state, I presume to know what's the displacement of the end of this structure. I know what's the current, the velocity at that time, and I happen to also know what's the acceleration. And what I want to know on the right-hand side of this screen are what's the updated values of position or displacement, velocity, and acceleration at this new time state, Tn plus 1. And the problem is I have three unknowns, right? Those three independent quantities. And if I were to only consider the equation of motion, this kind of discrete in time equation of motion, that only gives me one equation. I need two more equations to be able to uniquely solve for all of these three new unknowns that we've introduced. In fact, I need two more additional equations in order to figure out these two new unknowns we've introduced for the velocity and the acceleration. And it turns out that where you get those extra equations to solve for those new variables is precisely through this procedure known as time integration. It is effectively kind of a loose way of relating these different quantities, the displacements, the velocities, and the accelerations to one another through this kind of statement of saying, if I happen to know what's the displacement at the previous time state, and if I want to know what's the displacement at the new time state, I need to basically integrate the velocity field with respect to time over this particular time step. And I would have to do a similar thing. If I wanted to know the velocities, I'd have to integrate the acceleration with respect to time in order to find out what's the updated velocity at the new time step. So these are the two extra equations we have to introduce. And there's a whole stinking number of these kind of types of time integration formulas that you could develop. In fact, how exactly these integral or approximate integral expressions are evaluated is kind of a matter of art, if you like. But one particularly useful time integration formula, maybe you're familiar with it, is known as the Newmark-beta method. It is one of the most common time integration procedures that relates, again, some of these existing variables, let's say acceleration and velocity, in order to update the velocity and displacement at some new time step. And the formulas can get kind of hairy, but in general, the Newmark-beta method, which is a fairly general method, it actually is a parameterized method in terms of these two kind of tunable parameters, sometimes called beta and gamma. And the Newmark-beta method has some nice properties depending on how you set those two parameters, gamma and beta. You can get different methods that exhibit different behaviors, but in general, it's fairly simplistic. It's a single step method in the sense that you only need to consider a single one of these time steps in order to advance the old time solution, the displacement, velocity, and acceleration to the new time state. So there's some nice benefits that you get out of choosing this particular time integrator. But the Newmark-beta integrator, effectively, if you were to set these parameters in such a fashion, let's say gamma and beta, in the first case, let's just assume that we set this parameter gamma equal to 1/2 and that parameter beta equal to, I don't know, let's say also, 1/2, or more specifically, 2 beta equals 1/2. You can do a few manipulations of kind of these equations that I'd shown on the previous slide to get them into a nice, slightly nicer format. I've introduced this kind of intermediate term that involves basically trying to evaluate the acceleration, not at any particular time, Tn, but actually at some kind of offset time, which you could think of this offset time as being sort of an interpolated value of acceleration at some intermediate time between time Tn and time Tn plus 1. So this nasty term that involves evaluating the acceleration at one of these intermediate times, it shows up in these expressions for the Newmark-beta integrator. And in fact, where exactly you evaluate this kind of intermediate acceleration precisely, is how you choose these tunable parameters. I could choose gamma and beta to be some arbitrarily chosen combination of intermediate acceleration values. But if I choose, let's say, to evaluate gamma to be equal to 1/2, it's basically like I'm saying, choose to replace this value of acceleration with sort of the average acceleration from time tn and time tn plus 1. And similarly, if I chose 2 beta equals 1/2, I'd be doing kind of the same thing. Replace this expression with 1/2 of acceleration at time tn plus time tn plus 1. And making a few modifications and rearrangements, it turns out that you can re-express this whole kind of statement, this collection of equations, into the format of a procedural algorithm. So really, this particular setting of these parameters, gamma equals 1/2 and 2 beta equals 1/2, this is sometimes called the average acceleration method. Partly it derives from exactly that statement I mentioned before. If you set 2 beta equals to 1/2, then you're evaluating the average acceleration and plugging it into this formula in order to update the displacements in particular. So under this average acceleration method, making that substitution, we can actually approach updating these different variables in this stepwise fashion. And the first step actually involves introducing sort of another intermediate quantity, which I'll call the half-step velocity. So the first step really involves partially updating the velocity, not to time tn plus 1, the new time state where we want to know the velocity. We don't really know the acceleration at this new time state, so we can only go half the way there. So hence why we actually choose to just do this first half-step velocity update. But in doing so, we actually kind of simplify some of the ensuing expressions. So update the velocity, but only to its kind of half-step value by basically updating velocity plus delta t divided by 2 times the acceleration at the previous time state. So kind of like we're just integrating acceleration to come up with the new velocity. Now, at the next kind of sequence of steps, we would like to update the displacements by just integrating the displacements in time, that previous formula that we had. But it turns out that that expression actually involves not just this half-step velocity that we just computed from the previous step, but it also involves the acceleration at time tn plus 1. And the paradox here is that we don't yet know what is the acceleration at time tn plus 1. That, hopefully, we could determine in step 3, but only if we had determined already what the displacement at time tn plus 1 was. So unfortunately, if you're choosing this particular average acceleration time integration scheme, we find that steps 2 and 3 in this procedure are kind of coupled to one another. It's unfortunate that it basically means that we can't necessarily solve one and then the other. We have to solve them both simultaneously. And another way of saying that is that these kind of relationships are implicitly dependent on kind of the displacement and the acceleration. So unfortunately, that means we actually have to solve a system of equations and do a bunch of extra work in order to actually figure out how do we kind of do this kind of combined step to update both the displacements and also the accelerations in steps 2 and 3 in this kind of combined step, this implicit update. But if we did that, and assuming we kind of updated both this kind of new value for the displacements and accelerations, then we can come back and finally do that second half-step update for the velocities. So to update it to time tn plus 1, we take the half-step velocity and add to it the remaining kind of delta t divided by 2 times the acceleration at the new time step. Okay, so that's the implicit average acceleration method. Now, it so happens that there is another form of these parameters that we could choose that actually gets around this problem of this kind of requirement that we actually solve steps 2 and 3 simultaneously in an implicit fashion. And it turns out that if you choose gamma equals 1/2, but if you set 2 beta equals 0, then you actually find that there is no implicit dependence between steps 2 and 3. And in fact, you can just do step 2 and then subsequently solve step 3, and there's no implicit dependence going on. So in other words, we have an explicit relationship between all these quantities, and we can just kind of take all these steps in sequence, one at a time, just like there was kind of no tomorrow. It's great. We basically, can do this very efficiently just by decoupling these things and tuning this parameter. So why don't we always use this kind of nice, sometimes it's called the central difference method. Why don't we always use this particular time integrator? It seems like it has some very nice properties, right? It seems like we don't have to solve this implicit coupled system of equations, this implicit, system of equations. Why couldn't we use this all the time? Well, unfortunately, there are some drawbacks to this particular central difference time integrator. And it happens to be the case that if you were to implement this algorithm in some kind of, even for this simple one-dimensional harmonic oscillator problem, you would find that depending on how you chose to define this time step, this kind of value of delta t, that if you chose a value for the time step that's too big, then you would notice that you would get some vibration behavior, but those vibrations would start to grow exponentially. And you would basically run into this problem of an instability. So this is the limitation of this central difference time integrator method. It exhibits only conditional stability, assuming that you choose a sufficiently small value for the time step. And that's kind of a condition that you can mathematically show is actually related directly to the natural frequency of vibration of the structure. So assuming, however, you choose a time step that is sufficiently small, that's less than 2 divided by the natural frequency of this one-dimensional harmonic oscillator, then you'll guarantee that at least this algorithm will remain stable. It won't blow up as you kind of get to larger and larger values of time, and it works perfectly fine. So we've overcome that particular limitation, and we can kind of go ahead and use it. So that's actually kind of a nice feature, but nonetheless, something that we have to be careful about, because if we accidentally chose a value for the time step that was too big, then, things are going to blow up on us. And maybe it's useful to want to take larger values of the time step size for whatever reason. Maybe because if this constraint on this small time step size is so small, maybe because the natural frequency of the structure is particularly like high or something like that, then that can also introduce some limitations. So things to be aware of with these explicit or central difference methods. And there's another particular term for this algorithm, which actually has a nice interpretation as well. If I make a slight manipulation, rather than expressing this half-step velocity update in terms of the previous velocity defined at time tn, if I instead shift the definition for the velocities to be defined not at kind of like time tn and tn plus 1 and so forth, if I instead choose to define velocities at the half-step locations always, then I can kind of get rid of this extra fourth step, or in other words, consolidate it back into step 1. And I actually find that the algorithm looks a little bit simpler. All I have to do, in other words, is first update the velocity by just taking the old velocity at the previous half-step location, add to it delta t times the acceleration at time tn, and I get the new half-step velocity. Then use this new half-step velocity multiplied by delta t, add to the previous displacement to get the new displacement. Basically the same formula, just substituting different values here and here. So there's a lot of nice symmetry in terms of how it appears. And then finally, to update the accelerations, we have to basically solve our equation of motion in terms of the new updated displacements. So very, very simple 3-step procedure to do this algorithm, something that I think, would be very amenable to, a homework assignment, assuming I choose to kind of throw one final extra credit assignment at you. But actually the terminology that refers to how this kind of multi-step algorithm is carried out is kind of nice. And maybe you've heard this terminology before, but some people refer to this algorithm as the Leapfrog algorithm. And why do they say that? Well, it's kind of like you had, the displacements and the velocities are playing this game of Leapfrog. I don't know if you remember, or maybe you even played this game as a child, where maybe you and another partner are kind of like sequentially leaping over each other. I don't know, like one person crouches down and the person behind them jumps over them. And then that person who was previously crouching jumps over the next person. It's kind of this sequence of one person advancing over the other. And effectively, that's kind of what's happening in this algorithm. When you update, let's say, displacement from time tn minus 1 to time tn in step 2, effectively, you're kind of priming the velocities defined at the half steps to then be updated
from the half-step position, time tn minus 1, to time tn plus 1. But it can only happen if you've already done this kind of step. If this blue frog, in other words, were to take this leap, and then this orange frog could then subsequently jump over it in this sort of leapfrog kind of fashion. So the displacements have to be updated. Subsequently, the velocities. Intermediately, you also kind of do this update of the accelerations in order to update this kind of term that would show up to compute the updated velocities, but it's kind of like this sequential progression that allows you to update both of those two variables in this totally explicit algorithm that doesn't incur any kind of, I guess, coupled solution of any of these equations that you would have to do simultaneously, but which, again, has that kind of conditional stability limit that you have to be aware of. So that's all that we have time for today. We'll pick up on Friday. But if you have questions, feel free to visit in office hours. Otherwise, I'll see you Friday. All right.